How are y'all doing? Hope y'all are doing okay today. Did you have any questions on anything? Project number 4, Part C. Let me look that up real quick. Oh, that was the at least one, rather than that most or less than. Let's see. Let's see. What is the probability at least 80 prefer chips? Okay. Well, we established in 3 that I think we decided 8 out of 50 prefer chips, which is a probability of 0.16. And so we're using, for problem 4, we use p equals 0.16. N is 500. And then x is based on these values here. Okay. Like A, we do a Binomial PDF, and then B and C, we use Binomial Cdf. Okay. Now I did give you instructions for the at least, or the calculator instructions for the at least scenario. Let me point those out here. Yeah, here, this third option here, and I don't know if you have it 84 or 36 or 83, but this is how we calculate x greater than or equal to a value. Okay, from x to the n. What we actually do is, and you can see the command here, is basically what's happening. We use Binomial Cdf with n, p, and x minus 1. So you'll actually use, or Binomial Cdf, sorry. Yeah. But we'll instead of plugging x in like the first two do, we actually use x minus 1 here. So since it says probability of at least 80, we would plug in 79 there for x minus 1. Okay. And we do our calculation for that Binomial Cdf. Then whatever answer we get, we subtract from 1 right here. And that's the part that, okay, good. So it would be step 3 here for the 36. Use x minus 1 as the number of successes, and once you get the result, subtract it from 1. basically we're using the complement of this event, okay, by calculating the probability of 0 to x minus 1, which is what we're actually doing in that calculation, and we subtract it from 1. This complement represents the probability of x through n. And so that's the approach that we take there. So basically, this is 4a, 4b, and 4c. Okay. Oh yeah. Close that. Sorry about that. Okay. So let me present a scenario for us. It'll be a little bit different than what's on the project, but it'll be similar enough we can make a comparison. So, example, 20 people are surveyed, and 17 say they always use seatbelts when driving. Okay. If we ask 50 more people, what is the probability that at least 40 will use a seatbelt while driving? Okay. So the first part is kind of like problem 3, where we kind of establish the probability of success. So here we're saying our probability of success is 17 out of 20, which is 0.85. Okay. And so we continue with that here. Now we have the same probability of success, 0.85. We have 50 people that we're looking at, and we want at least 40 to be successes, considered successes. So, for this, that means we'll use Binomial Cdf. With p equals 0.85, n equals 50, and x equal 39. Okay, we'll calculate that and then subtract it from 1. Okay. So we go to second data, right to distributions, down to Binomial Cdf, option 4. Okay. Our sample size is 50. Probability of success, we said, is 0.85. X is 39. One less than the number here. Calculate that, and we get a value of 0.1199. That's good enough. 0.1199. And so we're going to subtract that from 1, which will give us 0.8801. And so basically what we calculated was the probability of less than 40, which was 0.1199, and then by taking the complement we now have the probability for at least 40, which is what we wanted. The binomial CDF, by its very nature, calculates the value or the probability of the outcomes from 0 to x. So if we want 40 or more, then we take 0 through 39, probability of that happening, and subtract it from 1 to get the probability of 40 plus happening. And this, it's completely based on complementary probability. Okay, good. Are there other questions? Okay. So today we're going to start chapter 7, which we'll be talking about normal distributions. Okay. We're looking at properties of the normal distribution. Now, when we look at a normal distribution, we think of it like this. Okay, and this is what we call a bell curve. We've talked about this before. And the idea is that right in the middle we have our mean, mu. And technically this is also the median and the mode. So we have our mean and median and mode all kind of at the same point in the normal distribution. Right in the middle at the high point of the curve. Okay. Now the area under this curve is equivalent to probability. And that's actually a pretty significant statement right there. It's largely based on calculus, actually. I know most of you probably haven't had calculus, so the good news is we're going to work around it. We're going to use our calculators to do that for the large part. There's also some tables in the back of the book we could use as an alternative, but I'll be sure to demonstrate both ways. But to kind of sum up, the area under the curve represents 100% of the probability. So if we want the likelihood, if we want the probability, if we have some value x here, the probability of an outcome smaller than x is equal to the area left of x, as I've shaded in here in the graph. Okay. So if we want to know the probability of an outcome being less than a certain number, and what we can already see is this is kind of like what we're talking about with our normal distribution, or sorry, binomial distribution in the last part of the project, and the last part of chapter 6. It's really the same concept, although now we're working with our normal distribution instead, and it does have some different properties we have to be aware of, and the approach is excuse me, is generally different in this regard because of the different calculations we'll need to make. So we no longer have a probability of success, we just have data, and then we have our statistics, our mean, and our standard deviation are probably the most significant ones here. But ultimately, we are looking for the area left of x with the shaded value. Okay. So we're not going to jump in how to find that area just yet, because you look at that and you think, well, this is nothing like what we remember from geometry, because we have this curved line here, and then we're trying to find the area, and everything we did in geometry back in high school had straight lines, and that was for a good reason, because it's much easier to work with than curved lines here. And that's why this is a calculus application, really, is because of the curved lines and how we have to use that to help us find the area of the curve. But again, like I said, we're going to work around the calculus. We're just going to do it either using the tables in the back of the book or our calculators, whichever one you prefer. Okay. So I'll be sure to show using the different calculators and the tables in the back. Now, we could also find the probability of an outcome being larger than x. We would just find the area to the right rather than to the left. So it's not really different in that regard, although we could actually use the complement there also. Actually, that's what happens in the back of the book, because the back of the book, the tables only show you the area to the left. So if we want the area to the right, we have to subtract it from 100% or 1. But we'll get to that eventually. We're not quite there yet. The shape of the curve is somewhat dictated by the mean and the standard deviation. So the bell curve shape is determined by the mean and the standard deviation. Okay, which again we designate those as mu and sigma. And in the book we have a couple of different graphs which illustrate this. In these first two graphs they have different means, but they have the same standard deviation. So one mean is here for one graph, it's right in the middle, and the other graph has a mean here. But the standard deviation is the same, so the shape of the curve is identical. Okay. Here we have two graphs with the same mean, so they both start at 0. But this one has a standard deviation of 2, and this one has a standard deviation of 1. And we see them have different shapes as a result. The one with the standard deviation of 1 is much taller than the one with the standard deviation of 2, which is wider instead. Okay, and we're not going to have to worry about that too much because we're actually going to look at a standard normal value rather than just a normal value, which means we're going to standardize it using some formula. But we'll get to that in a moment. Let's see what else. Now, I said the area under the curve is 100% of the probability, so it's actually the area is equal to 1 also. So we're just looking at the fraction of that representing the probability. And it's also true that the graph is symmetric, meaning that it's a mirror image on the left and right side. And we can see that in each of these four graphs. These are all mirrored left and right. And that means that 1/2 of the probability is on the left side and 1/2 of the probability is on the right hand side as a result, since we know that those add up to 1. Okay. We also have, and this is something we discussed very briefly back in chapter 3, we have the empirical rule that holds true. The empirical rule is kind of what we're depending on here to work for us. And so let me go over that again. That one's not quite as good, but we'll make do. Drawing lines on each side. It should be symmetric, but I suspect they're not. That's not bad. I'm happy with it. We know mu is right in the middle, and the distance between these bars is equal to 1 standard deviation. The same is true here in each of these other distances. So this is mu plus sigma, 1 standard deviation. If we go sigma units to the right, now it's mu plus 2 standard deviations. And then we have mu plus 3 standard deviations. On the left we have mu minus 1 standard deviation, sigma. Mu minus 2 standard deviations. And mu minus 3 standard deviations. Now the empirical rule says that within one standard deviation of the mean is 68% of data. Between two standard deviations of the mean, that means two standard deviations above and two standard deviations below the mean. There, that should represent, I think it's 97. Let me double check that one. 95%, good. It's good to check that. 95% of data. And within three standard deviations is 99.7% of data. Okay. And this is kind of basic. This is basically used as a guideline as far as how the tables in the back of the book were created and how our calculators actually find these probabilities that we're working with. You know, what we'll see here in the empirical rule agrees with what we'll see with the tables in the back or the calculator. Okay. So what that means is between here and here, this is basically from 0 to 34%, and this is also 34% here in this box. So they combine to give us 68% because they are symmetric. We know there's an equal portion here and here. So from here to here, it's a smaller number. It should actually be a little bit more drastic of a curve, but I wanted to draw a nicer curve, I guess. I don't know. We get from 68 to 95. That's an additional 27%. So there's 13.5% here, 13.5% here. 95 to 99.7 gives us 4.7. So there's a 2.35% here and 2.35% here. And then in the tails, there's just a little bit more on both sides, but it's actually getting closer and closer to the horizontal axis here. So in a way, this curve is an asymptote, or the horizontal axis is an asymptote where the curve will approach it but never technically intersect. Okay, and that's on both sides. So if you remember that from algebra class, we do have a horizontal asymptote here. Again, this doesn't affect anything that we need to do to be able to solve these problems, but I just want to go through the basics of what it is that we're looking at here. Okay. So that's the empirical rule. Let's look at the standard normal. What do we want to call that? Standard normal distribution. That's a good word. And this is something that we actually need to use. And the idea behind the standard normal distribution is that we have mean, mu, standard deviation, sigma, and we have a data value x. Then z is equal to x minus mu over sigma, where z represents the number of standard deviations a data value is above or below the mean. Okay. And what it allows us to do also is to compare two completely different data sets. Okay, now, so looking back at the empirical rule, basically the standard normal distribution allows us to pinpoint exactly where a data value is. But instead of being on this graph where mu is in the middle, the standard normal distribution looks something like this. In the standard normal distribution, the mean is normalized to 0, and the standard deviation is 1. So it's actually the same graph, but we've translated everything to where it's on a nice whole number scale, so we don't have to worry about the mean or the standard deviation. The mean is 0 and the standard deviation is 1, and it makes it a lot easier to work with overall. Okay. So we're going to be working with standard normal distributions, not just the normal distributions, but again, we like to use standard normal because it's much easier to work with. And again, our z value is now, again, the position. If z is -1, it's over here. If z is +2, it's over here. And then we find our area that we're interested in, and we go from there. This is probably a lot to take in right now without a lot of examples to go by yet, so please bear with me. Okay. Now at this point, I want to jump ahead to 7.2 where we actually start finding these things. I'm not going to give you any homework from 7.1. I just wanted to go through some of the basics that we need before we jump into 7.2, where we actually utilize the standard normal distribution. Keep that page handy. Okay. Here we are. Section 7.2, we're talking about applications of the normal distribution. Okay. Now, we still begin with this concept of z distribution. Okay, so we want to find out. Let me just start off with an example, and I'll demonstrate it on the two different calculators, and then on the textbook as well. Find the probability that z is less than 1.52. And we're going to go to 2 decimal places here because that's all the book has available in the tables it provides. We could go further on our calculators, but this should be sufficient for what we need. Okay, so first of all, we need to identify where z equals 1.52 is. And we go back to our standard normal distribution curve we looked at. 1.52 would be somewhere over here, about halfway between 1 and 2. And so we would draw a bell curve, draw a line about where 1.52 would be, and since we said the probability that it's less than that, we draw our line and then shade the area to the left. So we can call that 1.52, and again, it doesn't have to be perfect where we label that, as long as we know it, because it's positive, it's going to be right of this middle line. But how far right is kind of inexact. That's a good way of saying that. So as long as you understand which side it's on, that's the main thing. Okay, and we're just going to shade in this area. So this is the area we're trying to find, and it looks like, you know, it's bigger than 1/2. So at least we know a little bit about what to expect about the answer here. It's actually pretty large, it turns out. I think it's like 90% or thereabout. But we'll look at this on the table, and I'll also look at it on the calculator and how we can use those to find this result. Now, so let's look at our textbook first. Now, in the appendix, is that it? It is. Sort of. Oh yeah, that's it. This is page A11. It's actually right after the binomial distribution pages in the appendix of the book. One place, if you have a physical copy of the textbook rather than a digital copy, it's actually in there's a fold-out section back here, and it appears on this page also. Not that one, but there it is, kind of on the inside of that fold-out version. But also at the inside of the back cover is the exact same thing. Standard normal distribution. The fact that it appears in 3 different places should convey some of the importance of this as we continue to use these concepts throughout the remainder of the semester. Chapter 7, 8, 9, and 10. So. Now, I'm just going to use the one in the back of the book because it's the easiest for me to get to quickly without having some kind of bookmark, and I don't have anything really handy here I can use other than scratch paper. I guess I could use that if I needed to. Anyway, if you look in this table, there's all kinds of numbers here. We look on the side. It starts at z equals negative 3.4, comes all the way down to 0.0, and you can't really see that. Let me move this out of the way. Move it up. There we go. So you can see it goes all the way to 0.0 at the bottom, and on the right hand side we get the positive numbers starting at 0 and counting up from there to 3.4 at the bottom. Okay. But there's a whole lot of numbers here. Okay. These numbers are actually the probability. These represent the area and the probability. Okay. And if you notice on the top, it says the area to the left of a particular z value. Okay. Now, that's exactly what we're looking for. We're trying to find the area left of 1.52 here. Z equals 1.52. We want the area to the left. So, let me look at this. So the way that we figure that out is we come down to 1.5. Now, we said 1.52, but you'll notice that the numbers here only have one number after the decimal, all the way down. But here's 1.5. Now the numbers across the top tell us the second number after the decimal. So if we're on the line where it says 1.5, this is 1.50, 1.51, 1.52. Okay? So 1.52. And so this is the value that we need, 0.9357. And you'll notice that all of these are to 4 decimal places. We'll just round to 4 decimal places. 0.9357. Okay. And so we'll say area left of 1.52 is 0.9357. Okay. And so that's our probability, between 93 and 94% probability that z will be less than 1.52. Okay, that's how we do that with the table in the back of the book. Move this out of the way. I've got it's not new, I've had it for a while, but have my tablet here set up so I can see the chat. I guess you can't see that. So I can see the chat on here just like I have on my screen to the right, but the difference is I don't have to look over to the right to look at it. It's right in front of me now, which is nice. So I still have to look to the right to make sure I'm not like off the screen on my writing, but I'm going to try it out and see how well it works. This is the third class I've used it for today, and it's at 71%, so it's actually holding up pretty well as far as the battery lifetime. So this is a tablet that the school provided us at some point, and I have no idea why they gave us a tablet, but I figured I could put it to use. Anyway. At least I'm using it for the stated goal of education. So. Alright, so that's how we were able to look this up in the back of the book. Let me show you on the TI-36X first. Again, notice we're looking at a value of 1.52. Now the 84s, the newer, larger graphing calculators, actually are very similar to the 36X. In a way, it's a combination of the two, the 83 and the 36. But I'll talk about that after I look at these two first. Now, clear that. On the 36s, we'll press second in data and go over to distributions. But now our first two results, normal PDF and normal CDF. So we want normal CDF. So on the 36X, we press second data and select option 2, which is normal CDF. Okay. Now it says mean is 0, sigma, standard deviation is 1. So that's good. We just press enter there. And then it talks about the lower bound and the upper bound. Okay, now for the lower bound, what I would recommend is we know the graph continues all the way, it just keeps going because it's kind of open-ended on this side. But I would say we would use -10 as a lower boundary. We could actually use a smaller number than that, but by the time we get to -10, we already have like 8 or 9 places of accuracy after the decimal, so it's not a big deal. So we use -10 as a lower bound, and our upper bound will be basically whatever's on the right side of the shaded region, which is 1.52. Okay, so the right bound is 1.52. The lower bound is, we can say it goes to -infinity, but we can just use -10, and that is sufficient to give us the same number on the calculator. So we enter -10 as our lower bound, 1.52 as our upper bound, and calculate And we see the same number pop up, 0.9357, just like we saw right here. We actually see a lot more because the calculator will be more accurate in that regard. But again, just use the 4 decimal places, and that way I can make direct comparisons and show that they are the same on each format, whether you're using the tables in the book or the calculators. Okay. All right. So that's our 36. Pretty straightforward. The 84 is a lot like that, although instead of pressing second and data, there's a different button we have to press, and I'll talk about that in a second. Let's look at the 83s. These are the most complicated, it turns out. Okay. On the 83, we press second and vars. And the vars button is right here, and you can see right above it, it says distribution, DISTR. So we'll press second and then distribution. And this is just like we did the Binomial Cdf, except we don't have to arrow down so far. Again, we just want option 2, which is the normal CDF. Okay. Now what's different on the 83s is that we have to enter the whole command ourselves. So for this one, we have to put normal CDF, mu, no. Alright, messed it up. Our lower bound is first, upper bound is second, then mu, and then sigma. Okay? And these are all separated by commas. So we'll put -10, comma, 1.52, comma, mu is 0, comma, and sigma is 1. And those will always be 0 and 1, like we talked about over here, so we don't have to change those in the 36s. We don't. The only thing we have to do here in the 83s is make sure we enter the numbers 0 and 1. We press enter. And we see we get the same number as on the 36s, which is the 0.9357, 444, and so on. You'll notice that the graphing calculator actually goes 1 decimal place further than the smaller 36s, and this really just because of the amount of display area that's available. It's just a bigger display on the graphing calculator. That's the only difference. Okay, now for the 84s, we'd actually start the same way as we did in the 83s, which is second vars and then press option 2 for normal CDF. But then after that, it kind of guides us through the same way as the 36. So the 84 is kind of a combination of the two. I think the 36 and the 84 are really user-friendly. It's just a question of how we get there. One, we have to press second data, and the other, we have to press second in vars. So that's the only difference. So, yeah, 83, we have to be a little bit more careful about how we enter everything in and making sure that everything is accurate. We have to make sure everything's accurate on every approach, but especially so on the 83s. Alright. Hope y'all are not just completely glazing over at this point, and that this is somewhat useful. Let's see. Well, let's look at a different question. I'm not going to do it 3 different ways this time. We'll just pick one and go with it. I'll probably just alternate through the 3 different mechanisms I have. The book, and then calculator 1 and calculator 2. Okay. So Let's find the probability. Let's put that over. Let's see, that z is greater than this time, sorry. And we'll go 0.24. Now 0.24 is still positive, so it's still to the right of 0. Okay. And because we said greater than, we will shade the area to the right. Okay. Now, if we use the textbook with the tables specifically, in the book, again, the tables only show the area to the left. Okay? So we can look up 0.24. Here's 0.2. And we go across to where 4 is. And we see that we have a value of 0.5948. So 0.2 and 4. So 5948. Okay? So the area left is 0.5948. How would we find the area to the right? Since we only know the area to the left. This is the area to the left, we want the area to the right. Anyone have any ideas? Remember, yes, we know that the total area under the curve is 100%, or 1. We don't use percentages. And then we can just subtract this from 1, or 100%. Because this is a decimal, we should make sure we subtract it from 1 specifically. But this is like 59.48%, so we can subtract that from 100%. The area to the right is 1 minus 0.5948, which turns out to be, what is that, 0.4052? So anytime we want to find the area to the right, we'll just subtract it from 1. Okay. Now, I won't do this on both calculators, let's just look at it on one calculator. But we don't have to do the subtraction from 1 on these calculators. Because again, wait a second. Data, distribution, normal Cdf. Enter. Mean is 0, standard deviation is 1. Now, it completely depends on what we set as the lower bound and the upper bound. Now, the lower bound is where the shaded region begins, 0.24 in this case, and the upper bound is where it ends. Now, where it ends, we could say is positive 10. That's our upper bound. Okay, so we'll use a lower bound of 0.24 and an upper bound of 10. Notice it gives us the same result, 0.405, and this will round it up to 2. if we go to 4 decimal places. Okay. So the difference on the calculator is that rather than worrying about area left or area right, if we get the bounds correct, the lower bound and the upper bound, then the calculator does all that work for us. We don't have to worry about it, which is really nice, I think. And the approach would be similar in the 83s also. We just have to enter it in by hand rather than by being prompted like we are here. Okay. Let's look at another example. What is the probability that negative 0.74 is less than z is less than positive 2.19? Now, this one's different than the first two because now we're saying z is between these two values. So if we look at our graph and how that would turn out, negative 0.74 and 2.19, and we'll shade the area between them. Again, zero's in the middle, so we know the negative number's to the left and the positive number's to the right. And while we don't have to be perfect as far as where we plot them, we would want to show that 2.19 is further to the right than negative 0.74 is to the left. Roughly 2 to 3 times as far. But like I said, the drawing doesn't have to be perfect. I do encourage you to draw each of these on a bell curve. That way we can see what we're looking at, and hopefully that translates to a little bit better understanding of what we're doing, and also being able to recognize when an answer is correct versus when it's incorrect. This looks like it takes up a very large portion of the region under the curve, so it should be a pretty high probability. But we can't be sure until we go through and calculate the results. Now, if we're doing this in the table at the back of the book, remember the table only shows us the area to the left. So we could look up 0.74 and find the area to the left, and we can look up 2.19 and find its area to the left. How can we use those to find the area that's between these two numbers? Do you have any ideas? Area to the left of 0.74, negative 0.74, we can look that up. We can use the area to the left here and look that up. Oh, absolutely, Jacqueline. And that's how we would do on the calculator. I'm just saying, if we wanted to use the table in the back, or if we didn't have a calculator, how would we use the table at the back to find this? We'll do that in a second. Because unfortunately the textbook only tells us the area to the left of each number, so we know what the size of this area is here, and we know that the size of this area is here. So how can we use that area and that area to find this area? Anyone? It's okay if you're not sure. We know the area to the left is here, and we know this area to the left is here. So if we want the area between them, we take the larger area, subtract the smaller area, and that leaves the area between. Okay? So we have our bigger area to the left of 2.19. We subtract the area to the left of negative 0.74, and it should leave the area between. So for the table, we take the area left of 2.19 and subtract the area left of negative 0.74. Okay. So 2.19, let's see. .1 is here, and we go all the way to the right to get to 9. So 2.19, that is 0.9857. If you have trouble reading, that's okay. If you're looking at the book, or I'll have a printout for you for the exam, it should be a little bit bigger, of course. So we said 0.9857 minus, and then we look at the area left of negative 0.74. Negative 0.7 is down here. And then 0, 1, 2, 3, 4. And so that area is 0.2296. So we subtract those. 0.9857 minus 0.2296. And so that gives us 0.7561. Now, as you said, Jacqueline, we can certainly use the lower bound as negative 0.74 and 2.19 on the calculator, and that'll be much easier, absolutely. And so we go over to distribution, normal CDF, 0 for the mean, 1 for the standard deviation, negative 0.74, and you don't have to put the 0, you can just do negative 0.74. I'm just being formal at this point. And then 2.19 for our upper bound, and then calculate, and we get 0.76 or 75608. So it rounds to 7561 if we go to 4 decimal places. So we do get the same result. And again, on the 83s, we do second vars, normal CDF. Then our lower bound is first, so negative 0.74. Comma, upper bound, which is 2.19, comma, the mean, 0, comma, the standard deviation, 1. We should get exactly the same result here, 0.756088. But again, going to 4 decimal places, the 8 would round that up to a 1, so 7561, just like we saw. Okay. We have enough time to do an actual example. This is just kind of tease what's coming up. We've talked about finding probability based on z, but we haven't looked at any real world problems yet. So let me present you with one now. For example, IQ is known to have a mean of 100, so the average intelligence of a person is measured to be 100, with a standard deviation of 15. Okay. What is the probability a randomly selected individual will have an IQ higher than 120? Okay. This is where we use that Z formula that I wrote down a little while ago, and we haven't used it all since I brought it up. Let me rewrite it here. Z equals x minus mu over sigma. Okay. Now we need to create a z-score because z is what we're actually using to find these values. The z is a standardized value, and that's what we need to make sure we use. So mu we know is mean, and that's 100. Our standard deviation, sigma, is 15. And the data value that we're interested in is 120. So we want to know what's the probability that the IQ is higher than 120. So we'll calculate this. Z equals 120 minus 115, or sorry, 100 divided by 15. 120 divided by, or sorry, 120 minus 100 is 20. And then 20 over 15 is 1.33. Okay, so we calculated a z-score of 1.33. So we draw a bell curve. 0 is right in the middle. 1.33 is somewhat to the right. And if we're interested in the probability that a randomly selected individual will have an IQ higher than 120, which side do we need to shade it, to the left or to the right? To the right, yes. The higher than would be greater than, which is to the right. Okay. What will we use as our lower bound and our upper bound in this case? If we're going to use our calculators, which hopefully we will. Lower is 1.33, and the upper is 10. Yeah. 10 for upper and a negative 10 for lower if it just keeps going and it doesn't stop at any point. Yeah. That one takes a little bit to remember, but it's not too bad, I think. I used to use 4, but 4 was not quite good enough, and 10 is easier to remember anyway. Okay, so we go to our calculator. I don't know why I keep using this one. I guess I'm used to it. Second vars, normal CDF. Now, one thing, just a little shortcut we can do, we can just press the number 2 and it'll just bring up normal CDF. And that works on each of the calculators. So if you want to do that instead of arrowing down, you can just press the number we need. That works. Anyway, so we enter 1.33, comma 10, and then 0 and 1 for the standardized mean and standard deviation. And we get a result, which is 0.0918. Okay. Again, making sure we round to 4 decimal places. So that would be, the 5 would turn that 7 into an 8. Okay. Well, I said it correctly and then I wrote it down wrong, so that's my bad. Okay, there we go. Sorry about that. So yeah, a little bit better than 9% chance that we have selecting a random individual with an IQ higher than 120. Okay. So that's an example of of an application where we can utilize these standard normal distributions, and using our z-score we can calculate z and then use that to either look it up on the table or use our calculator like we did here. Okay. And again, depending on whether it says higher than or lower than or between, that tells us which scenario we're graphing here. Anyway, but it's important that we change our data value to a z-score, and that's how we get the z value. Because we can't plug in 120 and expect to get anything reasonable from the calculator. It has to generally be a number between -3 and +3 for it to be a meaningful result. And that's why we go through and we standardize it. Anyway, so for homework, let me see if I can make sure I turn off the calculator first. I'll leave it on. We'll just look at a couple of problems from 7.2 for now. I'm going to continue with some more of these application problems on Wednesday, but I wanted to go ahead and give an idea of how we actually use this today, so I don't just leave you with here's how we look up stuff in tables. That's that, and not have it mean anything. Let's see. So on page 374, look at 5, 7, and 9. And if you want to try out an application, look at 37. Although I would say in that case, skip A. Don't really worry about that one there. But B, C, and D would definitely be the ones you want to look at there for 37. Okay. Do you have any questions? Alright, so I think we'll just leave it at that, like I said, and we'll pick up where we left off here on Thursday. or Wednesday. Sorry, not Thursday. I'm already hoping it's a day later than it is. So you all take care, and I'll talk to you again on Wednesday. Have a good day.